Watch a modern developer work, and you'll see AI auto-completing clean Python code in real time. But underneath that productivity boost lies a serious risk. The same model generating an elegant function can just as easily write a hidden malicious script. In these massive public datasets, the models learn the syntax of clean functions and the architecture of malicious scripts simultaneously, absorbing every vulnerability present in their pre-training. Right now, we try to stop this by treating the model as a black box. We rely on prompt engineering or post-hoc filters to catch the bad code on its way out. But against a clever adversarial prompt, those surface-level defenses routinely fail. To actually secure these systems, we need a different approach. We have to look inside the architecture itself and pinpoint exactly where the model processes software security. Instead of just analyzing the text a large language model outputs, we need to map its internal structure. Malware detection behavior is localized. It is encoded within highly specific, quantifiable feed-forward network neurons. Our goal is to map exactly which nodes act as these security guardrails across three major instruction-tuned models: Llama 3.1, Mistral, and Qwen. Finding them requires running the models through a rigorous, four-stage mechanistic interpretability pipeline. The first stage is building a completely balanced testing environment, exactly 1,500 benign PyPy packages and 1,500 malicious ones. We have to isolate the pure harmful payload. Malware often contains massive amounts of stolen benign code to hide its purpose. If we leave that in, the model might mistakenly flag the benign clone code instead of the attack. We also enforce length-matched sampling. The benign and malicious snippets are cut to the exact same line count. Without this, the model could bypass actual code analysis and simply memorize file sizes. Next, we present the model with a multiple-choice question. Is this code A, benign, or B, malicious? To prevent the model from defaulting to an inherent bias for the first token it sees, we constantly swap the A and B labels. By stripping away file size differences and label bias, this dataset becomes a precision instrument. It triggers only the true security guardrail neurons, eliminating any confounding variables. With the data prepared, Stage 2 identifies which specific neurons fire during the test using integrated gradients and neuron conductance. This graph illustrates integrated gradients. It measures signal by accumulating gradients along a path, from a blank baseline, step by step toward the actual code snippet. We evaluate that signal with the target function, subtracting the incorrect answer's logic value from the correct one. This mathematically rewards a neuron for amplifying the right prediction, while actively penalizing it if it boosts the wrong one. The model then pools these raw output logits to determine its final classification. We are replacing black box guesswork with gradient-based proof. We now know exactly which neurons are reacting to the malicious code. But finding active neurons isn't enough. The network is inherently noisy. Many neurons are ambiguous, meaning they might facilitate a correct answer on one sample, but inhibit it on the next. To cut through the noise, we calculate an aggregate conductance score, which filters out those ambiguous nodes across the entire dataset. This leaves us with the absolute top 100 facilitating, or good neurons, and the top 100 inhibiting, or bad neurons. We now have the theoretical coordinates of the model's security guardrails, but observing them is not the same as proving they work. To do that, we have to intervene. In Stage 4, we move from observation to active manipulation. We introduce mathematical scalars to control output, S sub G for good neurons and S sub B for bad. This provides manual dials. The enhancer boosts good nodes while crushing bad ones, and the degrader does the opposite. If our mapping is accurate, adjusting these specific weights will instantly alter the model's ability to detect malware. Before adjusting, we record baseline accuracy on the test set. Applying the degrader condition, suppressing good nodes, doubling bad, entirely collapses the model's malware detection. Conversely, dialing up the enhancer pushes accuracy significantly higher than baseline. By exerting this level of deterministic control, we prove that these specific feed-forward neurons are the functional guardians of the model's software security knowledge. While this methodology works across the board, the location of these guardrails heavily depends on the pre-training recipe. In Llama 3.1 and Mistral, the active neurons cluster in the middle layers. In Qwen, they sit much later in the network. Knowing exactly which layer triggers this safety response has an immediate engineering application. Developers can implement early exit checks, halting malicious requests mid-generation and drastically reducing inference compute costs. This localized mapping also enables selective unlearning. Engineers can surgically edit the model's weights to patch specific security holes without degrading its general ability to write code. Mechanistic probing provides a path toward more reliable defense. By uncovering these internal mechanisms, we can move beyond black box testing to a more precise neuron-level understanding of how models detect malicious code.